Good morning, everyone. Thank you for the introduction and thank you for the invitation. I'm very happy to be here with you today. And I hope this presentation will be of interest to you. I'll do my best. And don't hesitate to ask questions during the presentation. I'll try to allocate the slot at the end, but to ask questions. So, as Chiang kindly introduced me, I'm CNRS research engineer at this laboratory, and I'm happy to give you today an overview of computational reproducibility, illustrated with examples from the medical imaging unit where I work at the CREATIS. Begin with, let me give you a first example that's extracted from an article published in Nature 2020. In our community, this is a very well-known and cited article. The authors selected one data set, okay, the same data set for everyone, and they provided this data set to 70 different research teams across the world and asked them to test 9 hypotheses, just like that. And we won't go into the details of the derivative part because I'm not an expert myself. Most of you are not experts in that too. But what I wanted to highlight here in the results. So the results here are brain maps. Brain maps like this. The particularity is that here, in each voxel, you have the proportion of teams that found an activation at that voxel. So what means here is that if you have a red color, it means that all the teams found an activation in that voxel. And if you're here in green, light, yellow, you're about 20% of teams that found an activation. So you see that it's very rare to be in red. These are the different hypotheses, hypothesis 1, 2, until 9. So most of the time, it's about 20 to 25% of teams that find the same result. So the article highlights the major variability among results, which was mainly due to analytical flexibility. So there were no 2 teams among the 70 selected that used the exact same workflow to treat the data that were tackle the hypothesis. So there was a high variability also among the analytical methodology. And last but not least, what I find also very interesting is that the authors asked the researcher, how confident are you that you have significant results? And even researchers that were well aware of the data had a marked optimism bias. That is, there was an overestimation of the likelihood of significant findings. And this is not particular to neurosciences. This is something that we are all subject to, I think, this optimism bias. So I think just being aware of it is important, so that we know how to handle our research. Okay, this was just to give you an overview of what can be, what's an example of reproducibility issues in brain. Starting from this, so let's figure it out. Let me show you. So my presentation will be structured in roughly 3 parts. First, I will be giving you definitions and categories in reproducibility so that we are sure that we all speak and think of the same thing. Then the main part will be focused on computational reproducibility. And at the end, I will try to sum up it and get a larger view of this. So definitions. There are quite a lot of definitions. Reproducibility is a sort of umbrella term that covers many other terms. The definition that I will be using throughout the presentation is the one that is more or less generally adopted by most of the communities. So if you want to have some more details, there's a nice article here in our 2018 about terminology and definitions. As I was saying, the one that we use today is this one that we consider data and analysis. And then we will look if we use the same data or the same analysis. And if both are the same, we'll speak about reproducibility. Otherwise, we can speak about replicability, robustness, or generalizability, where both are different. So we would say that reproducible research can be achieved when authors provide all the necessary data and the computer codes to run the analysis again, recreating the results. This seems quite straightforward, but is it? What would you consider same results? When are, for you, results reproducible? When do you consider they are the same? Give you a few illustrations here. So we're speaking about medical imaging, so I example of medical imaging. If you look at one result, okay, what we do here, you have another image of the brain. And in medical imaging, we often do segmentation, try to detect some structures in the image, like a tumor or lesions, like that. So here we want to detect this part highlighted in green. This is the input. We process the input to get different results. When we consider that these three here are the same, the easiest thing would be that these three files are bitwise identical. That means each bit is the same in the files. And this can be easily checked with mathematical functions such as checksums. But I'm sorry to disappoint you by saying that this is not very often possible. Most of the time, you don't have bitwise reproducible results. So what do you do then? Well, in that case, you have to find other metrics. And most of the time, it will depend on your research field and the exact application. For example, in medical imaging, here you can have nice scores or household distance or metrics like that that will tell you to what extent the image, the results is the same or not. Otherwise, you can go into statistical reproducibility, p-values and so on, and as I was saying, on specific metrics. Moreover, here we only look at one result, one output in particular. But most of the time in your papers, you don't have one result. You test the hypothesis. You have an analysis that is above a single result, and you have some conclusions. And when can you say that the conclusions are identical? This can be more or less ambiguous. Before going further into the definitions, I just wanted to make a quick reminder on accuracy and precision. I think most of you already know this better than I do, but I was thinking that students are here, maybe I should remind this. So on the x-axis, you have the precision, which is how close the measurements are to each other. So precision, here you have good precision because measurements are close to each other. Here you have bad precisions because measurements are scattered. Now, if we speak about accuracy, the accuracy on the y-axis, it is about how close the measurements are to the true value. But here you have all the values that are very close to the true value. You have high accuracy and high precision because they're close to each other. Whereas here you have you still have high accuracy, and it's at the bottom here that you have low accuracy because you are far from the true value. Why am I saying this? Because precision is often associated with reproducibility, right? So here we can see that we have good precision, good reproducibility, but that doesn't necessarily mean good results. If you have a software that will always output 2, you're sure to have reproducibility. You're sure to have precision. What about accuracy? Is that a good result? Why not? So reproducibility is important, but it's not, it doesn't solve the problem. It's not everything that you should see. So let's move on to still in the definition part of the presentation, see how reproducibility is defined otherwise, or what are different categories that we can define. Two researchers, Victoria Stodden and Leo Belli, classified the reproducibility in three categories: computational, empirical, and statistical. As I was saying, we will first talk about the computational part. And the recent paper by two French researchers from Diego and Robus gave another classification that I find very interesting, actually. It's about exact reproducibility that is close to what we call computational reproducibility. Is reproduction of strictly identical results as those of a previously published paper. Have the second case of statistical reproducibility, which is the reproduction of the results of a study under statistically equivalent conditions. And conceptual reproducibility, which is close to the generalizable definition here, which is reproduction of the results of a study under conceptually equivalent conditions. So you see here, it's generalizability studies. And I think this is clear to us all that this is where we want to go, this is what we aim for, but we need to go first through those steps in order to ensure that we can go further. Now, why would we have published? I think that with the examples given before, we already have an idea of where it's at. The first example I gave, Jim, I'm saying that even if the data set was fixed for use, the teams don't have same methodological approach. So from my point of view, I would classify sources of variability in three categories. At the top, you have the methodology. Then you have the analysis software, and then the expression environment. Let me say a few words about each of them. So for the methodology, this is CREATIS and so if you have a project, in this case, spectroscopy, you have plenty of steps that can impact reproducibility in the research methodology. You have the acquisition of data, then you have the data selection. How do you select them? Under which conditions? What criteria? You have data pre-processing. How do you decide to process that data? Then the analysis itself, and the instrument. This is part of the methodology and will definitely impact spirit is that if someone else is not the methodology, may or may not choose. The second layer, the analysis software. So I took once again examples from our debate. Functional MRI, there are quite a few different software that are used by the field that are all well known, quite used. As I said, this we can server same for advanced spectroscopy. But are you sure that using two equivalent software will provide the same results? Without talking about the parameters of each software, which is single parameter analysis for something else. Without talking about the different versions of the same software. Example later on. All this is variability and leads to issues. Last but not least, we have the execution environment that is very related to the operational part that we just afterwards. You have the software building, the kind of options, operating system underlying, the software run. This is something very important that we will not discuss today, but your result will depend on the generation of random numbers, if there are. The numerical instabilities that and the parallel. And then the hardware architecture counts. So that's for the first point about definitions, categories, a bit the overview of the so you have questions on this first one. fine? Perfect. So now we move on to the more technical part. Be prepared. So what is a computation? I will start with a few slides that borrowed from Conrad Kitson. At the end of my presentation, I gave some links to useful resources. It's useful resources. There are two links to two books, like books created by my French colleagues, among which Conrad Kitson and they have wonderful presentations of this why I to go to them. So this part is taken from Conrad, just to explain what is a computation. Have your data, have your code, that will produce outputs to you. But what's behind the code? It's your program that you know more or less, and the environment that you probably know less. And what's there? What's behind your program? Well, you have your program that depends on a multitude of packages that may have been built for different environments. You usually don't get to that part unless you are brilliant in science. And then at the bottom, you have the package manager, the build management. Why am I talking about all this? Because you use this thing here, which usually is not something you are well aware of, produce a result. And then what happens to this result? Let me show you a study made by a colleague that was was the CNRS researcher who practiced years in Canada. And a few years ago, he made a study. He took the same FSL version. So FSL, I will get into the data mechanism, a very well-known software in neuroimaging. He took FSL version 60506, and then he deployed the same version of the FSL on two different clusters. At that time, the clusters were CentOS and Fedora. He made the computations, and then here he showed the sum of binarized differences between 40 quotation classification containing two clusters. So, plainly said, you look at the red dots, and you see the differences between the results obtained in two clusters. So, opinion, he used the same FSL version. Why did he have such differences? So part of you have the question here. So if you dig into the problem, he monitored all the calls of the function points. And he realized that at some point, function exponential gave slightly different results. So you see here how many, the precision, but I think the seventh number after that. So this comes from two things. Mainly, numerical stability to floating point arithmetic. That this paper is just afterwards. Why do we have these different results? And second, you see that you have two different versions of JDC 2.5 and 18. And this is software variability, evolution of dependencies. And most of the time, this is something that you don't, not aware of, and you don't worry about. So now let's have a look into those two problems here. Let's start with arithmetic. Why do we have issues with that? Well, you know that real numbers can be infinite, but in computer science, you cannot have infinite precision. You have to make roundings. This leads to rounding errors. This is all standardized, and we should get the same results. Issues appear when we try to optimize. We try to optimize it independently at the pilot time, hardware levels, but normally all this is standardized and we should have the same results. However, it happens that we don't. or it happens that the expected output is not the one, the real output is not the one that you expect. I gave you here an example with the pi. It's a very simple one. I took A, I hope you can see it. A is 10 power 16. B is 10 power 16 plus 1. So what would you say would be the difference B minus A? I mean, if you do the computation yourself, it would be 1, right? What would you say is the result printed by Python? Yes, exactly. The difference is 0 because we don't have enough precision for this little one here that will be added on top of 10 power 16. So this is just a small example of how things go wrong. And we don't think things can go wrong because we have the... I have the idea that computers are maybe not perfect, but maths, it's standardized. I wouldn't expect such an error that is so easily made by humans, right? So this is just to raise a flag and say, be careful. There are round trip errors, and you should know how to deal. Okay, so things happen like this in real life, and I'll just say a word about Monte Carlo arithmetics because this is a very practical solution to simulate rounding errors and to study them with our tools. So Monte Carlo arithmetic will allow to inject noise into floating point operations like this. There are multiple ways of doing this, and the one that we investigated that I will tell a few words about it afterwards is random rounding, RR, which only perturbs the function output like this. There are a number of implementations of Monte Carlo arithmetic. The one that we've been using are based on Verificardo, which is a clan-based compiler that is used by the fuzzy library, which allows to easily use Monte Carlo arithmetic to inject this into your code, in the container, and see what are the effects. An example of a study that did this was once again Tristan Placard and one of students. These are two examples. I hope you can see how this. It's not fixed. It's not a fixed image. It's animated. And here you have the variability measured in cell populations produced by free surfer instrumented with Padawan. So this is the kind of differences we get. And I will show later in the presentation that this corresponds actually pretty well to real life developments that we have abilities. Okay, so I come back to the presentation to this slide before. We talked about numerical instability arithmetic, and now let's have a look at software variability. Where does it come from? So I took here a graph from Arnaud Legrand. I don't know if you are Python users. This is simply an illustration of all the dependencies of Python matplotlib. So it's just one package of Python, and it has all these dependencies. I won't go into detail, because just to illustrate that only for one package, you can have that many dependencies. And then just to have some fun, I took one of the XKCD images to illustrate how complex environment would be. So you can think here it's about the Python environment, as they can get complex. You can have different installation. You can have different versions. So here you have homebrew Python 3.6, Python 2.7. You can very easily have different versions of the same package in your system, and you may not be aware of which one you are using at some point. You can also have different environments such as Honda and virtual and so on. So this can be handled pretty well if you know what you're doing, but if you don't pay attention to it. So what if we had a solution to package all this mess into one package, one bomb, and use it easily and share it with our colleagues? So this is mainly what containers do. Containers are a way of packaging all the libraries in your executable and share it with others. You probably already have heard of Docker and Singularity, which now has become Container, which are the main container solutions that are known today. So how many of you have already used containers? What that is? How much? So maybe it's worth that I take a few moments to explain this. So how many of you know what virtual machines are? So let's think with containers. No need to make an analogy with virtual machines if you don't know them. So mainly you have your operating system, you have your operating system, and on top of that operating system, you can either have a virtual machine that contains its own OS, it's virtual, it's isolated, and you can put everything you want in there, and you can also share it with someone else. But virtual machines are a bit heavy because they connect to your own operating system. Quite many years now that containers try to do similar things, but without containing the OS. So they are much lighter. And they really are packaged their hardware that will all the binaries, the libraries, and the application. And they are executed. So in the case of Docker, they are executed with the Docker engine. In the case of Singularity Container, they are even lighter to function. And the idea is that these solutions allow you to package everything and run it on any other machine quite easily and use their own libraries that are inside there and not your own. Well, of course, for containers, you will somehow use some host libraries that are there, but most of the time, it's well. So how do you build such containers for images? This is quite easy. You have the recommended way of doing this are script files for Docker. They are called Docker files. So it's a script something like this. You just say what is the basis that you want to use. In my case, I'll choose basis for some costs. Linux Red Hat distribution. So here I say, okay, I want the latest version of CentOS as a basis of my container, my image. Why this is not a good idea? Any ideas? Reproducibility reasons. Why should I say this? Exactly. As I was saying, the software evolves. So today latest maybe 9 something, and tomorrow maybe 10 something else. If I build it today, I'll get a certain version. Tomorrow I'll get another one. So for reproducibility reasons, it's always good to fix the version of the software you use. So to be back to the way we can build such images, as you say, it's a real simple script, and you can get plenty of examples. You can get the basis to install what they need, where I need packages, and then I clone my Git repository, my code, and then I run main, it's the executable there, and I share my image with someone else. So they can launch what is service. How can I share? I can simply give the term to someone else, but otherwise there's a much practical way of doing it. There are hubs such as Docker Hub, so portals where thousands of images are shared. Well, this sounds very nice. I must admit it's very practical, and I personally use it regularly. But containers also have limitations. The first one is that they can very easily have bad losses. Let's say you build your Docker file, the recipe, but then you lose the recipe. Or within the recipe, instead of owning the source code and filing it inside the container, you decide to copy a binary file that has already been compiled in your machine. This is something you can do and which can work. But if you do that, you lose any trace of how that binary was built. You may lose trace of what are its dependencies and so on. So they become black boxes, which is an issue for transparency, just related. We'll come back to this later. And also, they may be difficult to update or build. Suppose you just copy the binary, but then you have a source, have an updated source code somewhere else. If you are not, then you clean the recipe, you may have difficulties, which is a longer term problem. Okay? But otherwise, on a daily basis, it's very comfortable to use containers. So these issues are quite well addressed by other solutions. They're a bit more complex, and we go into the detail, but there are solutions that solve these issues. The GIGS package manager, for example, is a functional package manager that will enforce, it will make you be very strict on how you build everything in there, have access to all the sources, everything. And by enforcing all this and by providing also reproducibility, building all this in a reproducible manner is answering all those challenges mentioned. And moreover, these packages are defined modules as exportable things. So once you did the hard work of writing the GIGS module for the users, it's very easy to use either GIGS as GIGS modules or as GIGS. So this was just to tell you that we come back at the two main causes that we mentioned at the computing level, why we have reproducibility issues. Because software evolves in time and because you have very limited abilities. This is quite well handled with containers. By putting everything in a package, ensuring that the same thing that is executed over and over again, you limit the influence of mainly of software dependencies. Same with GIGS. So this is something that has been used in the last few years by many platforms. I have here an example of a platform that was built in the desk and the study that was published in Nature this year. It's a platform that runs neuroimaging software on distributed resources. So you don't really have the you cannot manage everything that happens on those distributed resources. And what they did, on the left-hand side, they allowed local installation of the application. And on the right-hand side, they used containers, they used mirrorless containers. And what you see here, we come back to the brain maps. You have brains, and the colors here represent the variability. So if you are in red, it means you had some variability in the results. If you are white, it means you had no variability, all the results were the same. So you probably here, you can't see it very well, but on the right-hand side, you do have some light yellow here. It's not perfectly white. They did have some minor differences, even when they used containers, their infrastructure. And their conclusion was that these differences were probably due to hardware heterogeneity. Because if containers handle things at the software level, you still have the hardware level that may be different. However, they did not know to what extent hardware influenced that and why. Based on that study, we decided with colleagues from the Republic project that I will be introducing later on, we decided to dig into the problem and to understand what is the impact of hardware variability on the results in medical imaging applications. And this is a very recent study. We presented it at the ACM reproducibility conference in June this year, and we're actually very happy to get the best paper award on this paper. And we're also very modest, as you can see. If you're interested, I will present the results just afterwards. But if you're interested in the details, the preprint is available online. So our objectives in this study were to evaluate the impact of hardware variability and to correlate that impact to software and variability that had been studied previously. Okay, maybe just a very small break from questions. Do you have questions? I'm a bit puzzled because if we don't have questions, that means that either I'm very, very, very clear, which is strange, or that I don't get the right level of details, like you're lost. My presentation. No? Everything's fine? Should we go on like this? Okay. So for this study, we chose to evaluate reproducibility issues on the FSL-FLIRT application. FSL was mentioned before. It's a very well-known library of analysis for fMRI, MRI, and fusion brain imaging data. And it's a library, so it contains many different packages. We use the FLIRT one, which is used for linear image registration. How many of you know what this means? So affine brain registration means that we align a brain scan with another one through different ways. We have rotation, translation, scaling, and shearing. Here you have an example so that you can understand a bit what this means. On the top, you have the original image. In the middle, you have the reference. So we want to align the stop image on the reference. And at the bottom, you have the registered image. So the image on the top that we tried to put on the alpha. So this is what FLIRT does. Okay, this is the output. And the output of FLIRT is this nifty image, as well as the transformation matrix. So if we are in 3D and we have four operations, this results in a 12-degree of freedom operation. So you have this matrix, and why am I telling this to you? Because you probably don't care much about it. I'm telling this because for reproducibility study, we will look at these results, see to what extent these results were reproduced. Okay, so since we want to look at hardware impact, we needed to test quite a lot of different hardware architectures. And in order to do so, we used the French large-scale infrastructure, which is about 35,000. It's a research infrastructure that we can use as researchers. There for research. And we are very grateful that they provided to us resources on 9 different clusters. So these are the clusters. The name is not important. Some of them are in Sofia, some of them are spread all around France. What we are interested here is that we had different CPU models. We took both Intel and AMD, different models, different microarchitectures, and different ISCs, which is instruction set extension. So these microarchitectures come with a common set of instructions, and then you can have additional instructions that can be different from one CPU to another. I didn't know much about that before I started the study either, so don't be scared if this sounds very deep. Maybe it is. I won't go into details. I just want you to understand where the differences come. And they are related to floating point arithmetic. So I was saying earlier that those rounding errors or rounding differences may come from optimization at the compiler level or at the hardware level. So what happens here is that you have new instructions that will try to optimize previous ones. So ISCs, for example, the latest one here is AVX 512, and they work as layers. For example, AVX2 will support AVX, which will support SSE12, which is open diagrams. And what happened here is that AVX2, advanced vector extension, introduced a new instruction, which is the fused multiply add, which will do the multiplication and addition in a single operation. So that means a single round maps two rounds, which you can imagine that may have an impact on the rounding errors. So the difference is, you see, we took really different models, and at the beginning, we weren't expecting differences here, because we weren't aware of that either. And we'll see how this will impact the results. So what we did now, the global picture of our experiments, we took an open database, which is called OASIS, which contains 148 brain scans. And all those 148 brain scans were treated with FSL. And FSL, we packaged it two ways. I told you about containers, I told you about GIFs. First, we used, had a colleague in Strasbourg, and I remember that did a wonderful work by packaging GIFs, by packaging FSL for GIFs. And we deployed this on Grid 5000. And then we took a Docker image. And here we said, we will do like any common researcher that will look for a Docker image on Docker Hub. And these are images that are provided by the community. So we took the Docker image that corresponds to the same version, 16.5.1, and we executed this under the same conditions as the Gibbs one on Grid 5000. The Docker image, FSL was already compiled, so we didn't touch that. We had one simple executive. For the Gibbs part, since we built the modules, we had the means of modifying the compilation and adding flags if we wanted to do so. And since we used different architectures, we played a bit with the compilation flags, which are M-arch, like architecture, and we gave 4 different options, and I'll come back to them later, so that we see how this can impact themselves. So in total, we had 5 executables, 4 gigs on Docker, that we ran on 9 clusters. That makes 45 experiments times the 158 instances. So we did all that. We ran all that on Grid 5000, and we did something more. If we remember the Monte Carlo simulation, so with our colleagues in Canada, with Rostana and his PhD student, we also instrumented the Docker image. So we took the same Docker image with SSL, and we instrumented it with Verificardo. And what this does is that we'll replace all the mathlibs inside the container with mathematical function instrumented with Monte Carlo. That means adding some extra noise results. Remember, we used random rounding, so that means we modified the output. And we did this 10 times because it's random. We had 10 different results so that we can measure the variability introduced by the random output. Okay, so once we did this, I think this is the most complicated slide, so I'll try to explain it. Bear with me and ask questions if you have. We did all this, and now we want to compare the results. We have variability that can come from different sources. So here on the first column, we have the deployments. We had Docker or gigs. On the second column, we have the compilation flags. For Docker, we had one. For gigs, we had the default one, optimization, and then 3 different ones that were corresponding to the we used. Sorry for the mic. I think I'm moving it. I hope this will be audible. Then we have the actual people architecture on which we executed the executable. We have the ISC, the famous one, remember? And then we have the results. So what we did, since we had many files, we had 148 brain scans. Instead of looking at all results individually by one, we said, let's look at all of them. So with 45 experiments. For each of the 45 experiments, we created a tarball, a zip archive, out of all the 148 outputs. So we said, if the checksum of the tarball is the same, that means all the results inside the tarball are the same. If it's not the same, we can only conclude that there is at least one result that is different, and then we'll have a deeper look into it. But let's first look at the global checksum on the all 158 brain scans. Is that clear? Should I explain to you? We had 45 experiments. So here we had 45 experiments, and each experiment contained 148 brain scans. That means also 148 results. So we make a zip out of these 148 results for each of the 45 experiments, and compare their checksum. And what we notice here is that among the 45 experiments, we find 4 different checksums. So luckily, there are some that are strictly the same. Now let's see which are different. Why we have 4 different ones and not why do we have a single. So we see that we have 2 checksums for Doppler and 2 checksums for gigs. And what we notice is that for gigs, we managed to have the same checksum for all ICs and for all architectures if we compile standard no optimization flag. So if we have no hardware optimization for gigs, we get the same results for all architectures. But if optimizations are used, you see that on microarchitectures supporting AVX2, the famous fuse one like ads earlier, we get a different result, and the same for gigs. If we have optimization, we have different results for AVX than AVX2. Okay. So now, let's look deeper. What happens inside those big targets containing 108 results? 3 out of the 4 packages contain common results. So for example, for 3 of the 4 checksums, we always have 5 results that are identical. And for gigs and Doppler run on AVX and equals 2, we have 43 plus 5, we have 48 results common from the 2. So we have 1/3 of the results that are the same. Now, you probably ask yourself, okay, so what happens with the results? Why some of them are the same and others are not? Well, we did look deeper into what happens for each of the subjects. On the x-axis, you have the subjects. On the y-axis, you have frame-based displacement. Take it to the variability of the results. And here, the different colors show what was the cause of the variability. Was it due to hardware, to software, or a mix of the two? And what I want to point out is that for some subjects, like this one here, we have huge variabilities for all sources. For others, you have very small variability for all sources, whereas for others, have a mix of the two. Some sources will give large variability, some sources. And unfortunately, there's no clear indication in the data why this is so. I would say it's a bit like Monte Carlo arithmetic, it's random. So, but besides being random, what I find is very important, the message that I want to convey today is that it's very important to use large image databases. Imagine we only did that on one subject. This one, we did, okay, large variability all the time. it's important to test on large databases. And also what's important to see is that the input itself, beyond because here I said sources of variability, numerical hardware or software. But it's not only that, it's also your input data that will impact the variability. Okay. Okay. So a few more slides, and then I think big questions, and we will have a break. But let's finish on that. So now we saw these are differences. We measured them, but what is the impact on the output? I told you before that we want to register images. What will this give the registration level? And I also told you that in order to register the image, we have rotation and translation. So translation. So here you have translation in millimeters and rotation in degrees. And we plotted all the differences, and you see that the largest difference is given by this pink dot here, that is less than 6 millimeters and less than 0.2 degrees. And what does that do on a real image? So this is the output that corresponds to the pink dot here. This is how it moves. This is what it means, 0.2 degrees and 0.6 millimeters. Is it a lot? I have no idea. So why am I saying no? It's not a lot. It's really moderate here. I talked to the people. So Michael Stika, who's a CREATIS, helped us a lot in this use case because he was the expert on the vessel part. So we did this study with him, and he said, here is moderate. It's not a lot, but you need to know it's there. And you also need to know that this is a step that is done at the very beginning of the processing workflow. So what's the impact that this will have the diagnosis for the last step of the processing? We don't know, just evaluating this step. Okay, so a few statistical results. What we plot here is the comparison between rotation errors. For translation, it's very similar, so I won't put it twice, but rotation errors, depending on the different sources. So we have numerical with round rounding, hardware with Docker, hardware between gigs, and software, Docker versus gigs. And we see that they are very similar. We don't have significant differences between numerical and hardware with gigs, but we do have between numerical and hardware with Docker, and we also have between software and the others. So they are significant, but they are very, very small. See, they're really in the same order of magnitude. The same goes for correlation. There is, we computed this the Spearman correlation. There is no correlation between hardware, software, and numerical. However, I mean, unsurprisingly, we do have a moderate correlation between hardware with gigs and hardware with Docker. It's hardware effects, even if we measure it once with the Docker solution and once with the gig solution. Okay, so let's finish with the paper conclusions. We concluded that hardware, software, and numerical variability led to variations of similar magnitudes, but uncorrelated with each other, which is normal because they are individual causes. Rounding introduces perturbations of similar magnitude, which makes it a practical method to simulate both hardware and OS updates. Variations remain moderate, but might impact downstream analysis, as we'll see here. And both packaging solutions, Docker and gigs, managed to produce bitwise reproducible results on the same, when using the same package learned equivalently architectures. What's more, gigs managed to produce the same if we use the standard combination pack. And we have different outputs from one another to software variability. Docker images, as I was saying earlier, the one that we used was not real that close, but it was very transparent. Either we had to dig into it to find information on how the software was compiled. PICS ensures full transparencies. For the compilation options, we only studied the impact of the March flag related to the hardware, but as you may already be aware of, there are optimization flags like 01, 2, 3 that are very important, and they can also largely impact possibility. And in our case, hardware variability was due to AVX2 support. This is observational, and further work is for binary analysis. So I think, let me know how I am at time, but I think before moving on, I think we can take the break here, and then continue after the break. Or just, thank you.
Thank you, Sorina. Well, now I understand why the specialist says, say, don't believe anything you see on it. You have questions for the coffee. Good.
Wow, wonderful.
There's the attitude.
Thank you for your first part of your talk. I'm just wondering, I don't know exactly how to say this, but it's like, by constraining to have this exact reproducibility with software and hardware, we're removing all possibility of randomness and things like that. And is it good for accuracy and precision at the end, or to have some of this small difference can be good for the result and to obtain more diversity of precision?
Thank you. That's a very, very good question. And I'll try to tackle this at the end of the presentation. You are true. You are perfectly right. The idea is not to fix everything and to say we have no variation at all. If you have that variation, have it for a reason. There are some. So variation could even be good. That's why we're doing the simulation to see how this will vary. But my point of view is that you need to be aware of it. For people who are more into the physics part, we use measurement instruments. They are used to having precision interval, or they are used to having measures that are not 100% accurate or precise. Whereas in computer science, as I was saying, you don't question the result that much. So my point of view, the first point is to question the results and to be aware that there can be some variability. Now, if you for the logic of Ariane 6, I think it was very, very important not to have any variability and be very precise and know exactly what the values are. In our field, it's not that important to have bitwise reproducibility. You have to know when you need it and when you want to do it.
A little bit of two questions at once. One of the conclusions of your research is that in absolute values, the difference were not this great. They are significant, but it's okay. They can live with it. But when you showed this slide before that you repeated twice on this research that's shown the error on the exponential function, are these differences significant in regard to what you did? And if they are, do you think they could be maybe dealt with by better software testing during compilation?
Yes, so I understand correctly your question is about those. It's about this, the results of the metrics done in the study, and they were as moderate as in our case. Right? Yeah, it's more or less the same kind of conclusion. Differences are moderate. I mean, they won't change the final outcome. That's the conclusion. And about the testing part, yes, we do need better software testing. I think this gets better, but for research software like this one, we are not really used to having real testing like industrial fields. Does that answer your question? I will say a few words about testing later on. Subjects. Different subject. That's it. It could be linked to the data acquisition. We try to look, so I'm not an expert in the field. We kind of dig in, we have the data to see if there's any difference that is obvious to us. We didn't see it. We could put more into it. On another project, spectroscopy, we worked on quantifying the signal SNR ratio to see if it was linked to such things like that. It wasn't obvious either. So we didn't really find something obvious. I think you're right. It has to be someone into that.
Thank you. I have a question a bit linked to the last question. Maybe you said that, but I didn't catch it. On the variability between subjects, did you check or see the correlation between these kind of errors, or large and small errors, to the variation and the translation and rotation?
We didn't, but maybe we didn't search well enough. We had, to be honest, we had a quick look at the data, but we didn't really do studies like, we did a similar studies like the same spectroscopy. That's what was detailed. Here we just looked at the data. Person who was an expert in it, because I can look at the data the differences, but the person who looks who said this said it.
Yes, so if for a person who has who does a computation, so in an experiment, you repeat the simulation or you repeat the measurement several times and you get an error bar. So what would be someone who does a computation? How can they get an error bar? What would you advise to do? Because it's the same software hardware, so I get repeating the same computation is the same. Will it be somewhere, some database I can go and see, okay, from this hardware with all this, I get this error bar on my result? What would I do to get an error bar for the computation?
Let me check I understand correctly. Do you mean what to do if you get error bar, or do you ask how to get the
How to get, because you said, yes, during the measurement, we repeat measurement, we get an interval of precision, right? But in computation, you said we need to be aware that it exists as well, right? So how, I don't know, I just in the future, I do computation, I know it depends on things. So what error do I expect? How do I know? Without doing the same work you did.
It's a very difficult question because it depends. That's lots of factors. So, yeah, it really depends. We shouldn't take a concrete case. Let's say you develop your own algorithm and you publish a paper and you have results. So, most of the time you don't think of reproducing them yourself, right? So it would be your reviewer might try to reproduce them. Then if he or she does not manage to get these results, questions, but that's not. I would say that if you develop your own software and that has guidelines at the end, I encourage you to, since someone asked about testing, I encourage you to implement testing. It doesn't have to be exhaustive, but a few tests that allow you to run it over and over again and check that the results are the same. And what should those tests be? It depends on you are the person to expert. business result. If you develop it, then you can speak practice too. Yes.
Okay, so there will be some guidelines for,
There will be some guidelines.
I mean,
A few of
maybe
them.
in your talk or just in the future.
Yeah, I'll try to take this.
Thank you.
Welcome back. Should we start or should we wait a few more minutes? Okay, let's get started. So I think the most difficult part is done. The most technical part was the first session. Now I will try to give you a bit more of a background and tell you why I got here, why I'm interested in it. So the study that I presented before the break was done within the reproducibility project, which is a A&R project that will finish in a few weeks, actually in July. It was a project that I coordinated with colleagues from CREATIS, IPHC, and Lyon University in Canada. And our main objectives were to evaluate first and then improve the reproducibility of scientific results. And this is, I go back to the definition this morning when what we understood for reproducibility of scientific results was to have the same result when the code is executed with the same set of inputs. It's pretty basic, but as you have already seen, not that basic. And then we wanted to provide an integrated end-to-end solution allowing to launch a simple execution transparent manner, which is related to the new platform that happens just afterwards. So why, now I take things a bit backwards. This was the project. Why did I submit this project? I submit this project because I'm in charge of a platform which is called the platform, DAP, that allows researchers to execute medical imaging applications as a service. That means we take applications such as FSL that I will describe, and we import them into Leap. We deploy them with computing resources, and then researchers have to in the platform through a web portal and click on a button, fill in the inputs, and launch the application. So this was really done to help the life researchers. And at some point, I mean, DAP also provides access to computer resources. You have the chance to be part of the biomedical organization in a computing infrastructure. So we have access to plenty of computing and storage resources, but they are all very projects. So during my thesis, years back, I worked on optimizing the scheduling task of the resources. And then with time, I realized, okay, these resources are heterogeneous. We may not get strictly the same results depending on where the execution is from. So I was saying, okay, we offer this service to researchers, but to what extent can they trust the results that we are offering? This is how I came to the reproducibility project. So DAP is an open portal. I will make some publicity since I'm here. Don't hesitate to have everyone to create an account and access the applications. We are also open to integrating publications with participants regularly. We have more than 1,500 registered users that purchase 75 publications since the portal was in production. And I'm really interested in open useful science. And this goes a bit further than the computational reproducibility that I. So on the slide you have an example of white gray matter segmentation with another tool which is called reservoir. I was mentioning an integrated end-to-end solution. So DAP is a portal that provides applications as a service. also execution sharing. Since recently, things that you launch in EAP produce results, and then you may want to share this with the viewers, your colleagues, and we have a functionality that allows you to push those results directly to center. It's an open archive that was initiated by Sorina. So it's another org. It's similar to the cloud, but it's international level. And you can upload very various things, files, applications, now it's extensive software. Some of these larger. So within this portal, now we also support automation. There are notebooks, templates, Python client, the API to facilitate the automation of execution. Reproducibility. We also have reproducibility dashboard that you may be interested in. It's still it's in its infancy. The dashboard only supports 1 or 2 applications, but the aim here is to be able to easily compare results. Mostly results obtained in the AP, but you can also have your own data. The difficulty is that we need to implement the right metrics, and the metrics depend on the applications. Now we can compare images, files, so let's simply make to facilitate the comparison result. Continuous integration. So, we were speaking about tests earlier. A step further is continuous integration and integration with storage platforms. I won't go much into detail. EAP is a portal that currently supports mainly applications for medical imaging. You find that we're open. So we have applications for materials. This is a bit the motivation. I'm split my presentation, but since this was a course, I decided to which brings us to the larger overview that I promised. We spoke about reproducibility. Reproducibility is mainly producing the same results with the capacity. We were talking earlier, break. Some of you, what is the final aim? Or what we want to do with science? We want to reproduce exactly the same results over and over again. At the end, I think we want to be able to say, okay, my conclusion that I achieved from this data is that it should also be produced by researchers in different data. So how do we get there? There are multiple things, I would say. So if we go back here, you see you have data and analysis. Analysis for me is a very large term. It can encompass different things. It can start with software. Until now we just spoke about the implementation of stuff. So software. Software is something that is complicated. We have different layers. You can have scripts or names. I don't know how many are layers. So notebooks or interactive writing notebooks describe your experiment in patients at the same time. And for me, this is a bit the upper layer. Envisage that your application corresponds more or less to what you can describe the complicated applications to make the figures and draw the conclusions. But behind that, you have the core processing methods, our main algorithm that you know well enough. Behind that, you have this direct software dependencies, optimization toolboxes, data manipulation libraries, dependencies, and so on. So even at the software layer, you have multiple things. I try to give some good practices. Everything mixed, but don't hesitate to ask questions for details. I would say that at the software level, the first thing is to use Git or some system for version managing to manage and share code. How many of you use Git? So good. Then you should have clear licensing. Why? Because this also allows to define how you can share your code. You need proper documentation, which is very important. I forgot to add a slide that was very nice. Then code formatting and standards to facilitate the use. The use of permanent identifiers such as digital object identifiers, UIs, or software indices. To important is simple farming. So UIs, as their name says, they are identifiers, they are permanent. Not everyone can write the UI. You probably have papers, function paper, right? But there are different organizations that can provide one. Zenodo and specialists, they can provide UIs. Then material that is that I no longer change. It's permanent and tell you where you can find it. You're not allowed to modify it. Then this is for the development part. Now, once you develop the software, you need to deploy it. I would encourage you to publish version software packages using Python directly in GitHub. I also encourage you to use software containers. Yes, they have drawbacks. It's the first step before packaging correctly your application. I encourage you to write recipes so that you can rebuild and make this transparent as possible for you. And if you can, create these packages, which is probably long. Now, so here we had analysis, and I was saying analysis for me is the software, but above software is everything else. So it's a bit difficult to define it. From my point of view, analysis is everything you to produce the results that you publish anyway. It goes beyond running software, maintaining, registering, brain scans. It includes the methods, algorithms, everything you need to put in the paper. So methodology, software, and execution. So how can you ensure this possibility of the analysis? I don't know if you're aware of that. The people imaging community, there are checklists. Even if you're not in the field, they encourage you to have good because they give some interesting pointers. What can be done? What needs to be checked? The data level, software, training models. Now, you also have technical solutions for analysis. You have workshops that will ensure that you automate all the steps of your analysis. Such as thinking, Excel. You have the notebooks that are already mentioned. And then you have platforms such as PAP, and it goes into, let's have journals that are really into open science and reproducibility. So we have heard of having. So Habunduk, they have a very interesting view. Publishing and encouraging reproducibility. They spring tested code. Now, here we are, data. So my presentation mentioned data multiple times. Within the project, it's aware of the importance of data. It's able to tackle. So I'm not a data expert. Things that you need to be aware of. I follow the guidelines. These domains. The thing is that data is life. It's based on some variability. With data, it moves to so earlier that data needs to be pre-processed, processed, and so on. And have done studies that were not able to reproduce the results because the thing had changed. So, need to monitor changes. When data access and sharing is not possible, ensure proper description of the information. Why this is important? Because studies are made towards maybe the age of the patient have a importance. So say it's data is people, but you would be able to guess that it's kids, adults. Even if you're not able to share data, at least think about what is the proper metadata management. Use of data management platforms that are quite few of them. Have fun to make particular data management is science itself. And should make use of it. Do you know about the principles? Fair. It's a very important. You need to know about it when you leave this. FAIR stands for findable, accessible, interoperable, and reusable. Everything is more or less said. So, the acronym: findable, metadata, and data should be easy to find. If you did your study, I did a study with basis database. People should be able to find that database. Study if they wanted to. Accessible, that doesn't mean that it's freely available. It can imply authentication and authorization, okay? But there is a way of accessing them. Interoperable is very difficult. It's very, very difficult. But it's important to think of it. And reusable, it goes back to metadata and data. If they are not described, you won't be able to use them. And, well, I'm sorry, these are mostly general stuff. I don't know how much you did it, but these are important. Do you know about the TMP? Also, projects based on here. It forces you to think about how you manage the data. And it's often a pain. When you have to write it, you say, well, come on, I don't have time. It's quite fast. And in the end, you actually realize it's because we have so much data that we don't use it because we don't know how we did keep it for years. Data management plans force you to ask yourself questions. Maybe they're not all relevant to you. Some are, sure. So do think about it. You have to see once you have the chance to have a own form, there is a platform. Get that platform. They have templates that can help you to build your DMP. And if you have a project, such an ANR project for reporting, the project is automatically there and get all the administrative data directly. So we have to fill in the added value. Okay, so I don't know if you have more questions, discuss it afterwards. Now, I told you about reproducibility, I want to say a few words about transparency. I put here a citation that says that the one practice that in the university recommended is the transparent and fit reporting of both facets of the study, allowing the critical reader to evaluate the work and fully understand its strengths and limitations. Why am I telling you about this? Last year we had the chance to reproducibility. Our tutorial was about reproducibility computational. And before the conference, I was contacted by someone who was writing the conference, had a journal, and they were making publicity to the events that were going to take place at the conference. And one of the questions that we asked during the interview was, what would you say is more important, reproducibility or transparency? I was there thinking, I'm giving a tutorial. Why are you asking me which one is more important? Well, luckily, I didn't put it that way. It took a few moments to think about the question. And I don't think it's about what's more important than the other. They're both important. But I was giving the example earlier, if your code gives 2 over and over again, it's reproducible. But maybe it's completely off. Maybe completely mistaken. It's not because it's reproducible that that's good, that you validate it, right? So how can you validate it? How can you say if it's good or not? It needs to be transparent. It needs to give you this information that can allow a critical reader to evaluate answers the real question. So I wouldn't say, yeah, it's difficult to say more or less, but I think it's critical. I think it's important to talk about it because it's about reproducibility. So once again, it's not, yeah. And how do we do to foster transparency? I would say that for me, the 3 main things are documentation, sharing when possible, and version control, because this is how you take things. If you introduce a bug, it's much easier. Of course, there are many challenges which I think that problems because we can't always be transparent and share everything. Once again, we cannot share everything. Make the best you can so that others can understand your. I was mentioning validation when I was mentioning transparency. Validation for me is a continuous, never-ending problem. Once again, we're discussing about that. There's sort of a race publishing fast and well, but we don't always get the chance to do all the validation that we would like to do on our research. So earlier I did Strasbourg. Yeah, giving different reproducibility levels. We were talking also about statistical reproducibility. Part. Validation is also about validating coding software and using new databases. At what point your algorithm or your analysis is precise and accurate? It's bad. Both of them are important. And how do you validate it? Well, there are many studies about that. First, I think we need to define clear validation criteria. What does it mean to you to study is validated? Define and use formalized and transparent validation procedure and use standardized methods. Come back to data. It's a really important part. So if I sum up on computational reproducibility, I was saying that containers help mitigate the extent of environment introduced variability, but we construct the building environment. That's why if you have the possibility to have a look at the reproducibility of things and things. Parameterization and hardware mixed building response. I mentioned hardware, I explained a bit how this happened. Parameterization is similar in the sense that addition operations may not have the same order. So we have different rounding errors and we have parameterization. But now I come back to one of the questions that just earlier, some of you asked, should we eliminate variability? Should we aim for fixed results? Well, from my point of view, in the long term, software and infrastructures cannot be frozen. You will have variability. And most of our domains in our research, the aim is not to erase variability. The aim is to understand the sources and to take them into account. Eventually, if we can, to evaluate the difference. So, I think I'm a bit fast. I was fast on the first part that was. Computational reproducibility is a challenging problem. And the biggest problem is that it's often overlooked. They're not very. There are various possibly complex solutions. But computational reproducibility is only a small aspect of the larger issues. And transparency and validation are also essential. A few words on the additional point here. I don't know if you know it, but there's a French network on reproducibility. You can register if you want to be kept informed on the news. The two fun ones that I mentioned earlier, one was, I think this one was 2019, more or less the same kind of it. It's a generic one, and I think it's very useful for all domains. The second one, it's focused on practices and tools. It's a bit more technical, but you will learn much about the computational part that I just today. So they are very complementary. If you want more general things about logical principles, the first one. Two reproducibility tutorials. The first one is the one that I mentioned earlier that we did. With mine, hands-on material like the tools that allow to launch experiments. And another one that was also given by course. The learning way also has very good documentation in English. And there's also a French book. French. That you can find on Apple. So I have lots of acknowledgements. First of all, my colleagues from the project, graduates from India and from IHC. Then that's other people. So thank you very much for your attention. And do you have questions? We have time, we have plenty of time, so we can go into detail as much as you want.
Hello.
So maybe I can come back to the question just about part, right? The error bar thing. So at the beginning of the project, when I submitted the reporting for the project, one of the objectives was to evaluate the possibility and to produce some sort of error. Thinking of confidence intervals for given application. And I realized this was tremendously difficult. I wanted to provide a general cooking recipe on how to do that. And it was very difficult because first you need to define what you complete that interval and how you. It's also lots of statistical theory and statistics either, but I guess, well, colleagues of mine could have done that. And some Qatar actually did something similar. They put it into FI prep, which is education. And they studied the long terms. Said, okay, there are new versions of FI prep. It's regularly. And they said, okay, to what extent results are within that confidence? I think they have very nice study on that for the reference. In our case, we didn't really manage to get it. So at the end, we said, okay, the least we can do is to give the research flexibility to look at the differences in the results themselves. And that's the dashboard image that allows you to actually feedback. But the idea was to but depending on the application, what we want to define for each application data set that is pertinent for the study, then execute it different GAP resources. We can define metrics that we want to have some box plots and say my result is within the box plot. With this, give things. The intervals ideally would be any new input to have, which is very important. But what I can encourage you to do is, for example, same testing, implement tests as soon as possible when you build your software, when you start using it, and to combine this with continuous integration. Do you know about continuous integration? Yes. And if you are interested in going further, we can meet and we can see, do you have a certain application in mind?
Actually, I'm not thinking even about I know. But I'm using some alternative. Okay. exist. Wondering. I'm just wondering how these are themselves. Thank you all for something. I guess I can. It's not mine sometimes.
Well, that's a fact. This very is work done in that sense. Most of this search software we're using have such studies that we exist. I think this is something that is getting built step by step. This is something we are interested in. We want to do this to EAP with applications, different applications for the planet. I think this is something of interest. We can ask to the community if there are other people using that application. Try to do this.
No, so it's just sometimes I don't know, sometimes I look through my error, I think yeah, I also think they compare guys. But everything. In the parameters. Then also the question is that I still wondering if what precision you that wording just kind of the precision will be always in my opinion will be always higher than an experiment. So this they feel it always comparing. Anyway, our simulation our simulation will be precise. Maybe it depends on, yeah, I guess what, because you also showed that some data sets say the variations were high in capacity. Yeah, scans. Yeah, wondering if there's something that's with things.
Definitely.
Philosophical discussion.
Yes, I think most of the time, most of the time, these variations are respect to other factors. But we eventually get that managed to reproduce results from other papers. Unfortunately, this is very, very complicated. I mean, my slides of this many investigations, studies, study that is the percentage, how many publications you manage to reproduce. Fortunately, it's very, very low. So, it's not but the hardware, well, it's true that much of my presentation comes from that recent study we made because I was curious. Firstly, I was curious to see what is the impact of hardware with respect to comparison to the others. But most of our study, this is not the one that did change the results. Really. But what is it is to see in some publications that there are comparisons with other studies. So we say they're better than the others, 0.05%. And actually, that improvement, I always ask myself, okay, is that improvement significant? Is it in the error bar or is it outside the error bar? So I would say that most of the time it's fine, but when you compare, when your comparison goes that level, you should also ask yourself, okay, so if I do it again, is it generalized?
Right. So hopefully. The idea. And the it now. Yeah, so server.
It's a portal. It should be. Thank you for the question. Yeah. So this is the VIP main page. It's an open portal, and everyone can create an account. Everyone.
My first.
Wonderful. And as you can see here, there's a lot. There's some 20, 30 applications that are already available there. You can find the FSL clerk list of applications. A list of publications that have been produced by VIP users. And then if you log in, so once you log in, you have access to a certain number of things, among which applications for the MICAI tutorial, for MR spectroscopy. For MR spectroscopy, for example, we have different applications. CREATIS is an application that is developed by CREATIS. But we also have SSE12, software that is what Helen said is the software that is well known in the community and used by many people. In one of our studies, we compared the results between two software, two solutions, and we take one of the applications and show you how it works. Your imaging, for example, is put on free server. I click on the application I'm interested in, and then I just get this form where I can give the inputs. If I don't know what this is, we usually try to have an example that users who do not put the application can simply use by default. So there's a particularity for free server. It requires a personal license. So that means you need to upload your personal license to the IP. Then you just select the license. And then I simply have to click the launch button and Magic operates and FSL computation was launched. I used here a nifty file that was shared with all VIP users. Example can work, but you can use your own files. Then if I go back here, I can monitor my executions. So the one that is here is a thing that means it's running at the moment. I've launched it. That's me. Then I have other ones that have already finished. For example, let's take this one, it's finished and the outputs are available here. We also have a visualization plugin. It's only to help you see quickly. It's not really very developed, but it can allow you to see the result quickly. This is segmentation also. So this is how it works. You have applications that are available in services. You click on the application, you click the inputs, you launch it. This is the portal, and if you want to optimize this, we have our pipelines that belongs to script. Launching point. And something important, I was saying that we have multiple computing resources. For example, if I try again here. So here we can automatically parallelize. So here, if you don't want to treat one image, but 100 background study, you just put a list of inputs and here you automatically create 148 jobs that will be executed parallel.
Say something about the license. How do I get the license?
So the license was only for the free server application. The other applications do not require this. And for free server, you go to the free server page, register. It's free for research reasons, but you have to register as a person. Yeah, you get your person. But this is only for free server. All the others are license free. Please repeat the first part.
Data management, will buy many terabytes. They will store it in office. Do you have any advice on how we should proceed with that? Knowing that can be documents, slides, reports.
There are a lot of things that you need to consider. It's not one advice, but many of them. I would really encourage you to have a look at the auditor to start with. And in their data management plans, they do have specific questions. One of those questions are, what data will be acquired? Will you be reusing existing data? You buy one. Where will you store it? For how long? I think it's a good answer. Okay, which data will you store forever? Because you can't store it forever. For example, in reprov, we had plenty of experiments, some of them, and then we had plenty of results. And we were asked ourselves, okay, is it pertinent that we store all those results? Of course, if someone else wants to study again, they want to compare our results. Then again, you have plenty of results that were obtained in FCA. Is it really pertinent to store all those results on the long term? Maybe you can decide it's pertinent to store in the next 3 years. Or we also had access to the basis database that is open. But in order to work on that data, we had to do some reprocessing because the data was not in the right format. And then we said, okay, if we do this pre-processing and someone else will that study, we do have to save and share the pre-processed images because otherwise no one will be able to do exactly pre-processing as well. So our conclusion was subject. I mean, our conclusion was that we prefer to store it on the material data management solution, share it with everyone, and we allow them to read the experiments, but we did not store all the results.
Yes,
maybe it's not the right decision, but the thing is that you have to think about it, and you have to take into account that you will not be able to store everything in there. And maybe not all the data has the same importance, and you have to make choices.